Hi, welcome to part 2 of equilibrium. So this is going to be a fairly short, I hope, lecture component for this section because this is largely going to be calculations. We're going to be doing a lot of reinforcing of these concepts in our Zoom meeting where we work through the lecture problems. So I do encourage you to be either attending those live meetings or working through those problems on your own. So our goal for today is we're going to look at all the various ways that we can calculate equilibrium concentrations and the equilibrium constant. It's a really simple way to write out the mass action. It's often a little bit difficult to find the individual concentrations of the components. So we're going to look at the different ways to do that, and it's going to be dependent upon what information you're given up front in the problem as to which way you approach it. And some are easy and some are more complex. I'm going to introduce the term reaction quotient, which is Q. And Q and K are very related, except that Q is what's happening before you reach equilibrium. And so Q can tell you which direction your reaction is going as it's moving toward equilibrium. And Q is really very important for us if you're just taking amounts of everything and mixing them together and you don't know if the reaction is going in forward direction or if it's going in the reverse direction. So when you set up your K, you could have a very different K than what actually is happening experimentally. So Q is going to keep us honest with that. And then lots and lots and lots of calculations in this chapter. Practice makes perfect. You're going to be doing lots of quadratic equations. So this is something we're not going to do in this pre-recorded lecture. Might do just a little bit of it, but we're going to do the bulk of it in our Zoom meetings. So without further ado, let's just review a little bit from where we left off in part 1. So remember, we're looking at the law of mass action, and this deals with the equilibrium constant K and an equilibrium scenario. So we dealt a lot with H2 plus I2 goes to 2HI. And remember, this is my double arrow here that indicates I have an equilibrium. K I can write as a function of my products over my reactants, and we'll look at Kc. So remember, C is concentration, so I'm going to write these in terms of the concentration. My stoichiometry is going to apply, so I have 2 of these. So that's going to be to the second power over the concentration of H2 over the concentration of I2. And since both of these are understood 1, then these will both be to the 1. So this would be my law of mass action, evaluating K in terms of the forward direction of the reaction. But K is going to be, this means that I'm at equilibrium. So remember, at equilibrium, my concentrations of every substance isn't changing because my forward rate of my reaction is going to equal my reverse rate. So as these two combine to form HI, HI is decomposing to form H2 and I2 at the same rate. So I'm looking here at equilibrium concentrations. What I'm going to see at equilibrium is these are not going to change. I could write Kc, I could also write Kp, and Kp is in terms of partial pressures. So this is in terms of molarity. And this means I have molarity concentration. So these are all solutions, because if I have molarity, that implies I have a solution. This is going to be for gases only. And since these are all in the gas stage, I can write them this way. So this would be the partial pressure of HI, products over reactants still, partial pressure of H2 times the partial pressure of I2. K is going to be unitless, and I can relate Kc and Kp together using this equation here. And remember, delta N is the change in number of moles. So if delta N is 0, then Kp equals Kc. And that's the only time that that relationship can happen, is if delta N is 0. So in this case, I would take the number of moles of my product minus the number of moles of my reactants, and then that's going to give me my change in moles. In this case, delta N is 0, so my Kp and my Kc would be the same. This often doesn't happen. So calculating Keq, your equilibrium constant. This is the simplest method. And like I said, this is all going to depend on the information that you have about the system. So this is the simplest way, which you would want to opt for every time, but you may not be given this information, is if I know equilibrium concentrations of all reactants and products, and I want to ask to calculate Keq. So if I'm given equilibrium concentrations, that means I'm calculating Kc. or if I'm given equilibrium partial pressures of all reactants and products, and I'm asked to calculate KEQ, this is going to be KP. So these two are very simple ways because you're given everything. So your steps for this are you're going to write your mass action, substitute in your equilibrium concentrations or pressures, and solve for K. That's going to be the easiest way. So let's say in this scenario up here, I'm given concentrations. H2 equilibrium is 0.11 molar, I2 equilibrium is 0.11 molar, and HI at equilibrium is 0.78 molar. So I can take these values, I can substitute them into here and solve for Kc. So Kc is going to be equal to my products, 0.78 molarity squared over 0.11, 0.11. That's going to give me a value of 50. And remember, K is going to be unitless, so I'm just going to have a value here. And since I have two significant figures, I might put my decimal place there, or I might put this into scientific notation to denote that I have two significant figures based on my concentrations here. This is the simplest way. I could do it with concentration. I could also do it with partial pressures. If I was given those partial pressures, remember those would need to be in units of atmosphere, and then I could plug those in and solve for Kp. Now it gets a little tricky if it's not that simple. So let's say scenario number 2, let's say I want to calculate my equilibrium constant, but I'm given initial concentrations of all substances and only one equilibrium concentration. So this is going to be a little bit more complex. So here's my equation. Carbon monoxide gas plus hydrogen gas is in equilibrium with methanol gas. So that's my equilibrium reaction. My first step is I'm always going to write my mass action. It's just a good habit to get into when you're starting out. So always just write out your mass action. So my mass action here would be K is equal to CH3OH to the first power over CO and H2 squared. So that's my law of mass action. So here's some information that I give you. At 780 degrees Celsius, my initial concentrations of carbon monoxide are 0.500 molarity, and H2 is 1.00 molarity. And my assumption here is CH3OH is 0. So I don't have any of that yet. And my equilibrium concentration of CO is equal to 0.15 molar. And I want to calculate my KEQ. So I have all this information. I can't take these values and put them directly into here because these are my equilibrium concentrations and these are my initial concentrations. And so this value is going to go down when I reach equilibrium. This value is going to go down when I reach equilibrium. This value is obviously going to go up when I reach equilibrium. The only piece of information I have at equilibrium is CO. So these problems, you're going to approach them by constructing what we call an ICE table. And an ICE table means initial change in equilibrium. So that's your initial conditions, your change, what's changing, and your equilibrium. And we're going to be using these ICE tables for 3 chapters. So I would say embrace it now and know that this is going to be part of your lexicon for the next 3 chapters. What I do for ICE tables is I generally have the equation written down, and I'll just use the equation as my header for my ICE table, just so that I'm not rewriting things. But since I have all this junk in between, I'm just going to rewrite the equation here for you. So my initial conditions, so I'm going to draw a line here. This is going to kind of be my header. I'm going to deal with something for methanol, deal with something for hydrogen, deal with something for carbon monoxide. I'm going to have an initial set of conditions. This is my I and my ICE. I'm going to have a change. That's my C. And then I'm going to have equilibrium. So what happens once I've reached equilibrium here? So this is my table. All right, my initial concentrations, I'm just going to fill these values in. So CO is 0.500 molarity, H2 is 1 molarity, and CH3OH is 0 molarity. This is where if you do this under the reaction, it's going to help because your stoichiometry is going to come into play here. And so if I have my reaction sort of here as my header for my table, that reminds me that I have stoichiometry in here. So my change is going to be what's happening. These are going to reduce in concentration, and this is going to add in concentration. So I'm going to subtract my change, everything on the reactant side, and I'm going to be adding to my product. And so I'm going to subtract some amount here. So this would be X. I don't know what that is. I'm going to subtract some amount here, but since for every one of these, 2 of these, so this is where I'm going to bring that 2 down. This comes from my stoichiometry here, and then I'm going to gain X here. And so your coefficients for your X are going to come from the stoichiometry of the balanced chemical equation. So then my equilibrium is, I'm just going to add these 2 columns together. So my equilibrium here, we'll do this in purple. 0.500 molar minus X. This is 1 molarity minus 2X, and then this is X. And so what I want to do is calculate X. That's going to give me my equilibrium concentration. So this whole row here is going to be my equilibrium concentrations of my substances. Once I get these, then I can go back and fill them into here. Now, we're in scenario number 2, where you're given a really crucial piece of information that's going to help you. This here, that you have one of the equilibrium concentrations. And so that means that you are not going to need to use the quadratic equation here, which is kind of nice. So my equilibrium concentration of CO is 0.15 molar. That's this whole thing here. So I'm going to set this equal to 0.15 molar, and then I'm going to solve for X. So X equals 5 minus 0.15 molar, and that's going to give me 0.35 molar. So I have just solved for X, then I can plug X into everywhere. So X here is 2 times 0.35 molar. So down here, 1 minus 2X, this is going to give me 0.30 molarity. This is just X, so this is 0.35 molarity, and this is 0.35 molarity. So this one here, I would have taken 1 molar minus 2 times 0.35, and that would have given me 30 molarity. Now I'm just going to take these values here and plug them back into my law of mass action. So this is my equilibrium for CO. This is my equilibrium concentration for hydrogen. This is my equilibrium concentration for methanol, and then I'm going to be able to calculate Kc from there. So I had to do an ICE table to figure out what my changes and what my additions are, and then my Kc for this is going to be equal to 0.35 over 0.35 times 0.3 squared, and then that is going to give me 26. So my value for my equilibrium constant is going to be 26. Now I could also calculate Kp from here if I wanted to. So Kp equals Kc RT delta N. So if I asked for Kp, I could find delta N first. So delta N is going to go back to my original equation here. Delta N is 1 minus 3, which is going to give me a minus 2. So my delta N would be a minus 2, and then I would plug those in and solve for Kp if I wanted to do that way. So this is another way to calculate the equilibrium constant if you're given initial concentrations and only one equilibrium concentration. Then you're going to set up your ICE table, and then your third step is you're going to find X, and then you'll solve for Kc. And so I could do this with initial concentrations. My assumption here is that I don't have any of this, and then these are going to be my change. So your reactants are always going to be losing, your product is always going to be gaining. So this is going to be subtracting whatever is in your change column, and then this is going to be adding whatever's in your change column. Okay, so the third scenario is you want to calculate equilibrium concentrations but you're given K and initial concentrations. Now you need an ice table, and you're also going to have to solve the quadratic equation. So let's go back to our problem. CO plus hydrogen gas is in equilibrium with CH3OH gas. And let's say at 485 degrees Celsius, my K for this is going to be 67.8. My initial concentrations of CO is 0.67 molarity. My initial concentration of hydrogen is 0.50 molarity. And I'm going to assume that I don't have an initial concentration of this. And I want to know what are my equilibrium concentrations. So I'm going to calculate my equilibrium concentrations. I'm going to write down my law of mass action. So K is going to be equal to CH3OH over COH2 squared. So I'm going to write down my law of mass action, and then I'm going to set up my ice table. My initial concentrations here, I have 0.67 molar, I have 0.50 molar, and my assumption here is I haven't made any of that. My change, this is going to be reduced by some amount, this is going to be reduced by 2 times some amount, and this is going to be increased by some amount. So when I carry this all the way down, this is going to be 0.67 minus x, 0.50 minus 2x, and x. So now I need to find x. I also gave you k. So here's where I'm going to go back to my law of mass action, and I'm going to substitute all these in, because this is my equilibrium concentration for CO. This is my equilibrium concentration for H2. This is my equilibrium concentration for CH3OH. So I'm going to plug those in. So in this scenario, I'm just going to go back and I'm going to solve for x. I'm going to use the quadratic equation. And I'm not going to work all that through with you right now, but just to say that when we do the Zoom sessions, we'll be doing a couple of these where we work through the quadratic equation. Use your calculator for this. Don't try to do the quadratic equation by hand. It's miserable. Now what happens if I start a reaction and I have amounts of everything? So let's say I have this reaction going to N2O4, and I give you a K of 6.7 at 298 Kelvin. And I have a 2.25 liter container that contains the following: 0.055 moles of NO2, 0.082 moles of N2O4. And I want to know, is this at equilibrium? This is going to be a scenario where I'm going to use reaction quotient to figure out if the reaction is going in the direction that I think it's going. So Q is going to allow me to predict, because I don't know if I'm at equilibrium or not. I know that this favors, because this is fairly large, so it's going to favor the formation of the product, but I don't know at this amounts here if I'm going to be at equilibrium or not. I might go ahead and convert these into molarities, just because I know I'm going to need to use that. So I'm going to take moles and divide it by liter. That's going to give me molarity of NO2. This is 0.0244, and N2O4 is 0.0364 molarity. So I just have those molarities there handy. Q is going to allow me to figure out which direction it's going. I'm going to write Q a lot like I would write KEQ, but this is going to be my Q in terms of concentration. I'm going to write it just like my products over my reactant, N2O4. So it looks a lot like K, but it's something that's happening throughout. And so K is at equilibrium. If Q is greater than K, then I know I'm past that equilibrium and the reaction is actually going in reverse. If Q is less than K, then I know that the reaction is still going forward. So let's plug our values in here. So N2O4 was 0.0364 over 0.0244, and that whole thing squared. My Q is 61.1, which is much, much greater than my K. So this tells me that if I have these molarity of these gases, I'm actually not at equilibrium, because Q does not equal K, and since Q is greater than K, the reaction
is going in reverse. So opposite of how I have it written, I have an abundance of N2O4 more than I would normally have at equilibrium. So this is undergoing decomposition to NO2. So Q allows you to measure where you are in obtaining equilibrium. One, are you at equilibrium? Then Q equals K. If you are not at equilibrium but going forward, then Q is less than K. And then if you're past equilibrium, that means you're going in reverse as you have the reaction written, then Q is going to be greater than K. And so you'll want to find Q first, and then that tells you if the reaction is proceeding in the way that you have it written. Here it isn't, it's actually going this way. So if I wanted to really represent what was happening in this reaction, I would write it this way. N2O4 is going to 2NO2 with the concentrations that I was given for my initials. So that's the direction that my reaction is happening. Q will continually change as you move through the reaction until it reaches K. So Q is going to change throughout. So Q is just a way for us to look at a snapshot of information that we have and decide, am I at equilibrium? Is this an equilibrium scenario, or is that reaction still happening? And if it is, which direction is it going? And so you're going to set it up just like K, but it's not K unless they are equal to K. So we use Q a lot to allow us to discern where we are in a chemical reaction. So Q is important, and we're going to keep coming back to Q in the next 3 chapters when we talk about equilibrium processes. So this is where we're going to stop today, and I will see you guys in part 3 where we finish this chapter.